Everyone. I'm going to present our 2025 Mikai oral presentation, Unsupervised Cardiac Video Translation via Motion Feature Guided Diffusion Model. First, let us start with the most commonly used cardiac imaging modality, that is cine. As you can see, cine provides excellent structure information of cardiac that is used to analyze various cardiac functions such as cancer treatment, disease diagnosis, cardiac resynchronization therapy, and so on. Although cine is good for visual representation, it does not directly provide the cardiac motion information and normally require post-processing to extract the motion, which is crucial for tasks such as strain analysis or late myocardial activation detection. However, there is a more advanced modality called displacement encoding with stimulated echoes or DENS-CMR that directly encode motion during MRI acquisition. This provides highly accurate and quantifiable motion vectors that is shown as arrows. However, this process came at a cost of lowering imaging quality or structure information, as you can see from the magnitude images. This limit is application in several texture-based analysis such as segmentation or feature extraction. Hence, in this work, we introduce a novel motion feature-guided diffusion model that synthesizes high-quality structure information from the low-quality dense CMR images, which enable structure-based analysis over the dense CMR modality. However, this is not straightforward to achieve as cardiac imaging poses its unique challenges. Let us consider collecting CMR images of the patient as shown in the slide. Then we collect the dense CMR images from that same subject. However, as you clearly see, those videos have different spatial and temporal resolution. Therefore, those two modalities, CMR and dense CMR, does not naturally align since those two modalities have totally different acquisition protocol and acquisition time leading to spatio-temporal misalignment as you can see from the video. Although Gyan-based method can deal with those misalignment sequences, however, they oftentimes lack anatomical details and temporal consistency due to the lack of motion guidance. And diffusion-based video diffusion models require well-aligned CMRs for translation, which we don't have in our case. This is a brief background on video diffusion, where we first gradually add noise in the diffusion on the video during the forward diffusion process, and in the reverse diffusion process, we predict the additive noise using a denoiser. This is the overview of our proposed method. Given the input scene CMR, we introduce a pre-trained temporal registration based model on the latent temporal multi-head attention to first calculate the motion. Then we extract multi-level motion feature using our specialized spatio-temporal encoder that we call STME. This motion feature used as a condition to the video diffusion model to synthesize high quality cine-like CMRs during training. We will now focus on temporal registration part. Similar to classical registration, we also have encoder and decoder architecture in our temporal registration network. However, unlike traditional registration network, we leverage self-attention mechanism directly in the encoded velocity space to effectively capture long-range temporal dependencies of video motion. This enables a more expressive, scalable, and computationally efficient representation of cardiac motion dynamics by directly capturing global temporal interaction across all the time frames. Finally, we formulate the overall training objective of the network as shown in the loss equation. Now, I will discuss the implementation of our spatio-temporal motion feature extractor. Since temporal motion fields often contain complex dynamic patterns, hence instead of directly using them as a condition, we propose liberating multi-level motion feature that capture both coarse and fine-grained aspect of motion. To achieve this, our STME module first apply two consecutive 3D convolution layers with a nonlinear ReLU activation to the input motion sequence. Those feature maps are then passed through spatial and temporal attention layer respectively to extract fine-grained temporal motion feature of the motion pattern. Now we will focus on the conditional video diffusion. Unlike traditional video diffusion, we utilize the previously described motion feature into the diffusion process, since those features better guide the diffusion model, enabling it to generate more realistic and temporal consistent outputs. For motion conditioning, we employ cross attention in the decoder of the denoiser. During the forward, we first gradually apply noise to each video frame independently, and in the reverse process, we predict the noise based on the multi-level motion features. In the inference process, we replace our temporal registration network LTMA. Since the displacement fields are directly provided by the dense CMR sequences as we discussed in the introduction, moreover, we incorporated the dense magnitude information in the generation process by initially adding those dense magnitude images along with the pure noise. We employ the standard DDPM sampler to iteratively synthesize high quality cine-like texture for the dense magnitude images. We utilize cine dense datasets consist of multiple cine and dense scan from the same patient. We have used the FID and KID metrics for evaluating the synthesized image quality, and the motion consistency is evaluated by the FBD and FID. As shown from the table, video diffusion model GAIA outperform GAN-based approaches due to its progressive denoising with spatial and temporal attention head. Conditioning on motion further improve performance as seen in ControlNet. Our method achieved the best results by leveraging a specialized spatio-temporal encoder STME on the displacement field and training the video diffusion model from the scratch rather than fine-tuning as ControlNet. We evaluate the effectiveness of our temporal registration network and the STME block in this table. Our experimental findings demonstrate that the absence of latent attention causes degradation in the quality of the synthesized images due to the lack of spatio-temporal continuity in the motion. Finally, results further improved with the STME block since it enables to extract essential motion characteristics as condition to enhance synthesis quality. We also qualitatively demonstrate the effectiveness of our model. As shown in the left figure, each column represents an individual frame, while each row corresponds to a synthesized sequence from the different baseline method. Our approach produces myocardial sequences that both maintain spatial and temporal coherence across all frames. In the right panel, we show the synthesized video from our approach, and the cine videos are shown as structure representation reference from the same subject as dance. We evaluate our synthesis cine CMR sequences on a downstream segmentation task using a pre-trained 3D unit. Results show that direct inference on dense CMR sequences significantly degrade the performance, whereas our synthesis images significantly improve the segmentation accuracy. In conclusion, first we introduce video diffusion model to synthesize high quality cine CMR from misaligned dense CMR sequences. We also introduce latent temporal multi-head attention registration network for learning accurate, temporally consistent cardiac motion. And finally, we introduce spatio-temporal motion encoder, enabling motion feature diffusion model, improving synthesize quality and fidelity. Thank you, everyone.